A metal foam is a cellular structure consisting of a solid metal, frequently aluminium, as well as a large volume fraction of gas-filled pores. The pores can be sealed, or they can form an interconnected network. The defining characteristic of metal foams is a very high porosity. Typically, 75 to 95% of the volume consists of void spaces, making these ultralight materials. The strength of foamed metal possesses a power law relationship to its density, i.e., a 20% dense material is more than twice as strong as a 10% dense material. Metallic foams typically retain some physical properties of their base material. Foam made from non-flammable metal will remain non-flammable, and the foam is generally recyclable back to its base material. Coefficient to thermal expansion will also remain similar, while thermal conductivity will likely be reduced. Although there is a very large number of patents describing feasible topological structures, constitutive materials, and production methods, metal foams cannot be considered a commodity, and relatively few commercial producers are available worldwide of either closed or open-cell foams. Open-celled metal foams, also called metal sponges, have a wide variety of applications including heat exchangers, energy absorption, flow diffusion, and lightweight optics. Due to the high cost of the material, it is generally used in advanced technology, aerospace, and manufacturing. Extremely fine-scale open-cell foams, consisting of cells smaller than visible to the naked eye, are used as high-temperature filters in the chemical industry. Metallic foams are used in the field of compact heat exchangers to increase heat transfer at the cost of an additional pressure drop. However, their use permits substantial reduction in the physical size of a heat exchanger, and so fabrication costs. To model these materials, most works uses idealized and periodic structures or averaged macroscopic properties. Metal sponges have very large surface area for their weight, so catalysts are often metal sponges, such as palladium black, platinum sponge, spongy nickel, etc. Manufacturing routes. Open-cell metal foams can be manufactured by several ways, especially through foundry or powder metallurgy. In the powder method, space holders are needed, as their name suggests. They give space to the open pores and channels during or after the foam-making process. In casting processes, foams are made by replicas of open-celled polyurethane foams used as a skeleton. Closed-cell metal foam was first reported in 1926 by Meller in a French patent where foaming of light metals, either by inert gas injection or by blowing agent, was suggested. The next two patents on sponge-like metal were issued to Benjamin Sosnick in 1948 and 1951, who applied mercury vapor to blow liquid aluminium. Closed-cell metal foams have been developed since about 1956 by John C. Elliott at Bjorkson Research Laboratories. Although the first prototypes were available in the 50s, commercial production was started only in the 90s by Shinko Wire Company in Japan. Closed-cell metal foams are primarily used as an impact-absorbing material, similarly to the polymer foams in a bicycle helmet, but for higher impact loads. Unlike many polymer foams, metal foams remain deformed after impact and can therefore only be used once. They are light and stiff, and are frequently proposed as a lightweight structural material. However, they have not yet been widely used for this purpose. Closed-cell foams retain the fire-resistant and recycling capability of other metallic foams, but add the ability to float in water. Manufacturing routes. Metal foams are commonly made by injecting a gas or mixing a foaming agent into molten metal. Under certain circumstances, metallic melts can be foamed by creating gas bubbles in the liquid. Normally, gas bubbles formed in a metallic melt tend to quickly rise to its surface due to the high buoyancy forces in the high-density liquid. This rise can be hampered by increasing the viscosity of the molten metal, either by adding fine ceramic powders or alloying elements to form stabilizing particles in the melt, or by other means. Metallic melts can be foamed in one of three ways: by injecting gas into the liquid metal from an external source, by causing an in-situ gas formation in the liquid by admixing gas-releasing blowing agents to the molten metal, by causing the precipitation of gas which was previously dissolved in the liquid. In order to stabilize the molten metal bubbles, high-temperature foaming agents are required. The size of the pores, or cells, is usually 1 to 8 mm. When foaming or blowing agents are used, they are frequently mixed to the metal in the solid state at a powder form. This is the so-called powder route of foaming, and it is probably the most established. After metal powders and foaming agent have been mixed, they are compressed into a compact, solid precursor, which can be available in the form of a billet, a sheet or a wire. Production of precursors can be done by a combination of materials forming processes, such as powder pressing, extrusion, flat rolling. Composite foams formed from hollow beads of one metal within a solid matrix of another, such as steel within aluminium, have been formed in a laboratory, and are showing 5 to 6 times greater strength-to-density ratio, and over 7 times higher energy absorption than previous metal foams. Stochastic and regular foams. Stochastic A foam is said to be stochastic when its porosity distribution is random. Most foams are stochastic because of their method of manufacture: foaming of liquid or solid metal, vapor deposition, direct or indirect random casting of a mold containing beads or matrix. Regular A foam is said to be regular when its structure is ordered. One of the technologies developed to produce regular foams is by CTIF. This is a direct molding method in which molding produces a foam with open and regular pores. Alternatively, regular metal foams can be produced by additive manufacturing processes such as selective laser melting. Plates are used as casting cores. Their shape is customized for each application. This manufacturing method allows for perfect foam, so-called because it satisfies Plato's laws and has conducting pores of the shape of a truncated octahedron Kelvin cell. Direct molding foundry can produce complex shapes, including massive portions and foam. Regular foams gallery. Heat sink with copper foam. Crash box including aluminium foam with big porosity, aluminium foam with aluminium sheet, header, steel metal foam. Applications. Design metal foam can be used in product or architectural composition. Design part gallery machined metal foam. Design heat sink with regular foam. Coffee table with large poured aluminium. Mechanical orthopedic uses foam metal has been used in experimental prosthetics for animals. In this application, a hole is drilled into the bone and the metal foam inserted, letting the bone grow into the metal for a permanent connection. For orthopedic application, foams from metals such as tantalum or titanium are often used, as these metals exhibit high tensile strength and corrosion resistance with excellent biocompatibility. Clinical studies on mammals. A notable example of clinical use of metallic foam is with a Siberian husky, named Triumph, whose back legs received foam metal prostheses. Studies on mammals have shown that porous metals, such as titanium foam, may allow the formation of vascular systems within the porous area. Orthopedic use in humans. More recently, orthopedic device manufacturers have started producing devices that use foam construction or metal foam coatings to achieve the desired levels of osseointegration. Automobiles. Metallic foams are currently being looked at as a new material for automobiles. The main goal of the use of metallic foams in vehicles is to increase sound dampening, reduce the weight of the automobile, and increase energy absorption in case of crashes, or to combat the concussive force of IEDs. As an example, foam-filled tubes could be used as anti-intrusion bars. The metallic foams that are currently being looked at are aluminium and its alloys due to their low density. These foams have a high stiffness, are fire-resistant, do not give off toxic fumes, are fully recyclable, have high energy absorbance, have low thermal conductivity, have low magnetic permeability, and are efficient at sound dampening, especially in comparison to lightweight hollow parts. In addition, partial addition of metallic foams in hollow parts of the car will decrease weakness points usually associated with car crashes and noisy vibrations. These foams are cheap to cast by using powder metallurgy. In comparison to polymer foams, metallic foams are stiffer, stronger, and more energy absorbent. They are more fire resistant, and have better weathering properties when considering UVL, humidity, and temperature. However, they are heavier, more expensive, and non-insulating. Metal foam technology has also been applied in the treatment of the automotive exhaust gas. Compared to the traditional catalytic converter that uses cordierite ceramic as substrate, the metal foam substrate can offer better heat transfer and exhibits excellent mass transport properties, offering possibilities for using less platinum catalyst. Energy absorption. As honeycombed metal foams are used for stiffening a structure without increasing the mass of the structure. For this type of application, metal foams are generally used in closed pore and aluminium. The foam panels are glued to the aluminium plate to obtain a resistant composite sandwich, locally and rigid along the length depending on the thickness of foam. The advantage of metal foams, whether regular or stochastic, is that the reaction is constant, regardless of the direction of the effort. Indeed, the foams are homogeneous. They have a plateau of constant stress after deformation. This deformation may go up to 80% of crushing. Thermal, T and AL listed several criteria to assess a foam in a heat exchanger. The comparison of thermal performance metal foams with materials conventionally used in the intensification of trade first shows that the pressure losses caused by foams are much more important than with conventional fins, yet are significantly lower than those of the bed of beads. The exchange coefficients are close to beds and ball are well above the blades. Foams offer other interesting features, thermophysically and mechanically. Very low mass, large exchange surface, relatively high permeability, relatively high effective thermal conductivities, good resistance to thermal shocks, high pressures, high temperatures, moisture, wear and thermal cycling, good absorption of mechanical shock and sound. Pore size and porosity can be controlled by the manufacturer. While foams have a great potential for use in compact heat exchangers, heat sinks, and shock absorbers, their industrialization is, yet, limited due to the high cost of foam replications. Also, their long-term resistance to fouling, corrosion and erosion are insufficiently characterized. From a manufacturing standpoint, the transition to foam technology is not easy because it requires new production and assembly and an important reflection on the architecture of the heat exchanger systems. An exchanger with more foam will be successful if the architecture adapts exchanger rather than install the foam in a known architecture.